All right, so welcome back. And now we're going to start discussing something called convolution. And convolution is both a mechanical process and a useful and extremely powerful property of the Laplace transform that we make use of to help us through this. But we're just doing this sort of conceptual explanation behind convolution first, at least this afternoon. So we're going to take a little side trip and we're going to back off a little bit. We know that in terms of our model, what we have X. We model the system as such. We have a system and the system response in time. Remember, they're all time domain systems. The system response in time is some ht, which is a differential equation and an exponents and all the like. Xt is the inputs coming in, which are real world signals, however they happen to be defined, and we get a real world type of output coming out. But we know already, we've started to model, and we know that in terms of the transfer functions, if xt has a Laplace transform of xs, and yt has a transform ys, and the system has a transfer function hs, that the relationship between ys, hs, and xs was this equation, a product. Right? So we know this. Right? Because we've been using this little property all the way down. But what exactly is yt in terms of xt? What is the relationship between y and t? In other words, what is the real world relationship for that? And to discover that, we will go back to a little bit about how we did sampling. Remember when we were talking about sampling, we said that to sample a signal, you took the continuous time signal, and you multiplied it by this thing called an impulse train. And then what that did was that it picked out the values of the function at those particular points. And those are what we call the samples. And we defined the whole process, the signal, in terms of mathematics, the whole process of sampling as taking the continuous time signal and you multiplied it by this pulse train. The pulse train was a series of impulses, so that in shorthand, what we got, the answer that we got, was our samples in shorthand was a series of numbers multiplied by delayed impulses. Remember, every impulse like here, I can simply write that as delta t minus whatever that point is, right? So if this was the 15th impulse, it would be delta t minus 15t and so on. So it's a whole sum of those, and n is running from minus infinity to infinity. So if a system has an impulse response, so the impulse response, we said in the Laplace domain is hs. This impulse response, of course, is a Laplace transform of the response of the system to an impulse. This, of course, has some equivalent in time, ht. So what we're saying then, in shorthand, is that if xt, if my input to the system is an impulse, then the output for the system is the impulse response, which is ht. Clear enough? Stop me if anything isn't making sense. Huh? I want to make sure you have it. Make sense? This is by definition. All right? So if the input to the system is an impulse, the output of the system is going to be the system's impulse response, which is ht. So if the input to the system is some impulse, but instead of the impulse occurring at t equal to 0, the impulse occurs at some t equal capital T, then the output of the system will be the same impulse response but delayed by the same capital T, because we are dealing with linear time invariant systems. Remember, we went through that already. So if I put the impulse today, I get my impulse response. If I put the same impulse tomorrow, I'm going to get the impulse response tomorrow. It's just delayed by 1 day. And same way, if I put a weighted impulse, which is this, so instead of a unit impulse, it is an impulse that has a magnitude or energy, a weight of A, then the response to that particular impulse is going to be A times the impulse response whenever that occurred. Yeah? Again, this only happens with linear time invariant systems. So if we put in an input looking like this, then our sampled signal, remember, is a series of weighted impulses. This here, this is a series of weighted impulses. So what would be the output of that? Each impulse, each weighted impulse is going to give an output. So each of these, so at t equal to naught, we're going to get h naught. At t equal to t, we're going to get h t. Then t equal to t minus, little t minus 2t, we're going to get h, sorry, it should be a t minus here. Let me just clear that. Right? So at t equal to 0, we get ht. For the impulse at t minus t, we will get the response ht minus t. For the impulse at t, of course, multiplied by x, the appropriate x value, so whatever x at t would be. And then for at t minus 2t, we will have ht minus 2t by whatever value x at 2t was. And so you keep going on. So in other words, the output response, this is the input, the output response is going to be a series of weighted impulse responses. Each of these is an impulse response. So the first impulse gives you ht, the second one gives you hnt, and so on. This is something called a convolution sum. Right? Notice the form. It's an x multiplied by an ht minus, it's an xt multiplied by an hnt minus nt. All right? That's the sort of format of it, and they call that a convolution sum. Everybody following so far? Yeah? Great. So for the discrete time system, therefore, the input-output relationship is that ynt is the convolution sum of the inputs and the system response. Remember, each of these is a little delta, right? Is a weighted input. This, every time you put one of that into here, you get an h coming out, appropriately delayed. So xt minus 1 will give you an ht minus 1. Xt minus 75 will give you ht minus 75. So the whole total response over all the inputs, however big long that thing is this thing that we call a convolution sum. Right. So now, remember what we're trying to find? We're trying to answer this bit here, right? In the continuous time domain, what is yt in terms of xt? We're seeing that in the discrete time domain, that the output-input relationship is a convolution sum of the input and the system responses. So we can already get in mind that something going to, when we start to go to the continuous mode or the continuous time domain, that is going to be something along the a similar line. And how we get that is simply by this. We have this that we just derived, right? And I can approximate, if you remember when you were doing when you were learning to do integration, you remember what you did was that you took something and then to find the area underneath it, for instance, you took 2 points and you separated them by some distance. So you calculated one value, you calculated one value, and then you let these 2 points get smaller and smaller. And eventually you worked out the integral. You're going to take the same approach here. So I could take a continuous time signal and I could represent the continuous time signal as a series of rectangular pulses. Okay, so all I'm doing is to break up this continuous time signal into a series of these things, right? So each of these is a rectangular pulse. Okay, and as you could see, if the width of the rectangle gets smaller and smaller, it's going that x hat, the approximation is going to slowly get equal to xt. And we define each of them as a pulse. Remember early on last week, we defined the unit impulse as something whose width was a and whose height was 1 over a. And we made a very small so that the area underneath this thing remained as 1, but it got infinitely narrow and infinitely tall. So therefore, if I were to take the same approach and call this pulse, just give it a fancy subtitle, which is delta t by delta, which is a width. Each pulse I could define like this. So the delta at this little definition here, which is hard to read, delta sub delta t, right, is telling me that this is this bit here, and delta is telling me that's the width, right? So they hide by the width. That's the definition of the pulse. So the pulse down the road, the pulse occurring at instant k would be delta t minus k delta, which is here. And of course, the width is still delta, right? And I could define the entire sequence. So this entire series of rectangle pulses here, I could define as a sum of all of them. Fair enough? Yeah? Good. And so this is it here then. So I could take this, and therefore the whole staircase approximation becomes a series, a sum of them. Okay, giving me some issues here. And guess what? What am I going to do? Just like we did in calculus and way back when, I am going to let delta now start to get very small. So as delta gets very small, right? As delta gets very small, those pulses get smaller and smaller. And then we go back to here now. If each of these, like we did in the case before, each of these is a pulse. Okay, x hat t at some point is a pulse, and if I put that into the system, it is going to generate some response. Yeah, just like we did for the samples before. So each of these, if I put it into a system, is going to generate some response. So I put it into the system, each of them. So if xt is delta t, that's the first one, then if I put the delta a series of delayed ones like this, then the output is going to be a sum of all of those individual pulse responses, which is just what we did for the discrete time case. And I am going to make delta very small. When delta becomes very small, the pulses, remember each of the pulses is height, it is delta wide and 1 over delta tall. If I start to make this very small, then it becomes 1 over delta, it becomes very tall and very narrow, just like our perfect impulse before. And if you remember, so these points now, you get more and more of them. So the k delta, as this decreases, t minus these points become more and more, so the pulses become closer and closer and closer until eventually the pulses run into each other and we have continuous time. And what is a continuous time summation? A continuous time summation is an integral. So instead of summing over a set of values, they integrate continuously over a set of values. What is a continuous time signal? Instead of the signal occurring at instances of delta, it is now occurring at a continuous time. And the impulse responses for each of these, remember, you could represent this as millions and millions of little impulses. So each of these million and million of impulses gives you an impulse response. So in the limit, you have that the output now is the product of the continuous time input and the impulse response of the system, but you're integrating it over all time. And we call that a convolution integral, which was, I guess, you could have derived from, if we went back to here, when we had a convolution sum, if I start to make t very small, which is what I'm doing here, but just to make the connection with the continuous time domain, if I make the t's very small, then the individual responses become continuous, and you'll end up with the convolution integral here. And that now leads us to the answer to our first question here, which was that in the Laplace domain, we know that ys is equal to hs. In time, we know that the actual response in time is that it's a convolution of x and the impulse response. And we write it in shorthand using an asterisk. So the output in time is the convolution x convolved with h in time. And as we see the properties that we have, h, that is the same as this. Right? X convolved with h and h convolved with x is the same thing, because we're dealing with linear time invariant, and we're going to examine those properties as well. But this is the important thing, that convolution in time is the same as multiplication in the S domain. So instead of having to do this kind of integral in time, if we are in the S domain, all we have to do is to do a product. So you can solve the integration by doing it, by converting everything to the S domain and then doing the integral there. Is everybody following that? Any questions there? Everybody clear on what that is? Want to make sure. Right, nice. Okay, so I wanted to get that done today because we're going to, I just wanted to get that, at least get your mind wrapped around it, because next time, today's lecture will be a little bit short, so you could review some of the stuff that we worked on as well. Next time, we're going to sit down and actually go through how you do this convolution. First off, some of the properties of it, and then actually doing it, because it isn't always, remember one of the things that I mentioned before, it is not always possible that you can get either HS or XS. If XS, for instance, was something discontinuous, if XS is going on all the time, it's fine. But what about if XS looks something like that? Getting the sorry, if XT, my mistake. If XT looks something like this, which is a piecewise continuous signal, trying to find XS is going to be difficult. So in situations like that, you have to have a mechanical way of doing it. All right, and that is what we're going to lead up to, how you do the convolution mechanically. The next lecture is going to take us through that. And just in case, because people tend to have some little issues with this and then want to know, well, why we do it. And there's a particular reason, and we'll get to that as well. But there's some videos on some other things that we'll put up on this side that you can have a look at. But I think wait until we actually go through it in class in some more detail before you watch those and see. Look at what we're doing, answer the questions first based on what we do, and then we can go and look at the videos if you're still stuck. Yeah? So questions. Any last questions here? Okay, so at this point in time, you are capable of attempting problem set 1, and maybe even parts of problem set 2 already, but mainly problem set 1. And I would like you to at least try those. We will try to have a, oh yeah, the course outline. My mistake, I was supposed to upload that today. Thank you for the reminder. I'll do that as soon as I'm finished here. So the problem set 1, you should be able to do that and attempt it. And I will schedule a, what do you call it, a tutorial session just to run through those quickly. Of course, it only makes sense, tutorials only make sense if you have something to ask a question about. All right, so try that, review the stuff, and then we will continue this on Monday, and then do some examples on Tuesday next week and continue along the way. All right, we have convolution, we have block diagrams, and block diagram simplification and so on to get to, and then some other properties of system responses to look at, which would tidy up the sort of system response and the Laplace transform revision all in one. Yeah. All right. So you had an early-ish class today, and that's also to give you a little chance to catch up on some stuff. I don't want to necessarily rush everything through and just put everything on there. I want to make some time at least to make sure some of these things that seem to give people trouble in the past, that we spend a little bit of time on it, and that you have some time to at least think about it going forward. All right. So that being said, let me